Real quick, pre-calcsters, ask me who's killed a warden in here.
Who's killed a warden?
Not me.
Oh.
Got him. All right, so yesterday we started talking about polynomial functions. Two things that we need. You got to be able to draw it without picking up your pencil. That is the lazy way to say what?
No work.
Continuous. Good. Okay, additionally, we can't have sharp corners. We just need smooth curves. That's it. Now, when we're looking at a function like this, yesterday we left off saying that there's only a couple possibilities. The leading coefficient could be positive or negative. Those are the only options. And the biggest power of x, or my degree, could be even or odd. That's it, right? Okay, for today's stuff, we are going to think about the two easiest possibilities, and we're going to try to summarize this. And we saw the idea of some calculus in here. If you notice up on this whiteboard, just so you guys can see, was when I asked this question yesterday and said, what does the function do as I go far to the right? Was everybody okay with that concept? And the notation's new, but are you okay with the notation? Here is exactly what we did in calculus today. Notice it's the exact same thing. We're doing some fancy stuff. If you guys remember the difference quotient from chapter 1 that we just threw in there that one day, you've already done a bunch of this. We're just putting it together. Now, our focus in here is not the calculus, but you do recognize some of the calculus already because we introduced it. For this, we're going to make a little table, and I need your guys' help. We're going to consider a table where we're thinking about a function, f of x, that is just simply written as a sub n, x to the power of n, plus dot, dot, dot. Don't care. I only care about the very first term, because it will give me the leading coefficient, but it will also give me the degree of the function. The only two things that we care about. Okay, so as we're looking at this, we're going to make a little table. It's going to be 3 row by 3 column, just so you guys know, 3 by 3. And it doesn't really matter which way we do it, but I'm going to just separate it here, and then I'll make the other size as large as I need. For this one, are we going to talk about the coefficient or the degree? There's not a right answer. Should this be the leading coefficient or the degree? Degree, deal. So check it out. The degree is what letter here? N. So there's only two possibilities. N is even, is one possibility. And then I'm going to leave some space so that we can draw, or at least write a few things. And the other possibility here would be what? N is odd. Okay. When we think about any polynomial function, and that's a really broad statement, there's two of the easiest ones I can think of that I'm going to always rely on. What is the first odd number? 1. Okay. Can we all envision, either on your page if you have to sketch it, or in your head, the graph of y equals x to the first power? Yes. Okay, we're going to get a little disco here real quick. What does it look like? Just that, right? Okay, this is an odd. 1 is an odd number. That's it. Everybody cool with that? Okay, odd. Deal. All right, now we had the other side of things we had to worry about, though. If we're talking about the degree here, what was the other thing that we were talking about? This is called the what test? Okay, so I also need to talk about the leading coefficient. What is the leading coefficient of this function? Almost. A sub n. There's only two possibilities. A sub n is less than 0, which is a fancy mathy way to say what? Negative. And in contrast with that, we have a sub n could be greater than 0, which is just a mathy way to say positive. Now, somebody in here already remembered the math dance just now. Okay. Parts of it anyway. We're going to think about even and odd, and I'm always just going to use 1 and 2 as in my mind, okay? So you guys just told me that if it's 1x, it goes like this. Okay, as you go really far to the right, which is like as x goes to infinity, what does the value of my function actually do? Increase. How high up does it keep going? Infinity. So do you guys agree that if we graph y equals positive 1x to the first power, it goes up and to the right forever? Okay, there are two ways that we can do this, and I need to make sure that we can do both. Okay, in red, I'm going to show you the way that I've traditionally taught it, but this class hasn't traditionally been an AP course either, so we need to be a little bit more formal. Here's how I've always done it. When we look at n is even, we'll do odd, sorry. and positive. So it's all the way down here. The graph of y equals x looks like this, yeah? Which means as you go really far to the right, my function goes really far up. This is going to feel weird, but as I go really far to the left, and I'm getting goofed up as I'm thinking about it. Is this right for you guys? So as I go really far up, as I go really far to the right, it goes really far up. What about as I go really far to the left?
Down.
It goes downward or decreases forever. So when we do this, I'm not just going to connect it as a line. I want very clearly up to the right, down to the left. Okay, and there's a reason that I'm leaving a gap in there, but this is a really convenient shorthand to make sense of it and not have to be really wordy with it. If we want to be wordy, and sometimes we will, I want you to help me with these two statements. As x approaches infinity, f of x, the y value, approaches what? If it keeps going all the way to the right, it goes all the way up to how far up? So that's a weird question, I get it. Here's x. How high up? Louder. Infinitely high, right? So as x goes to infinity, my function f of x, the y values, also go to infinity. Infinitely far to the right, infinitely far up. That's all this says. What about as x goes to negative infinity, which is just saying infinitely far which direction? So you're right, but how about just on the x-axis? That's infinitely far to the left or to the right? Left. My function goes infinitely far downward, which is what you answered, Christina, and you're absolutely right, but it goes down forever to negative infinity. Okay, here's where I need your honest feedback. I much prefer just using this notation, 100%. The College Board and the AP test people will not like that notation. Thoughts? We'll have some time at the end of the year to review before the AP test everything. Anybody adamantly opposed to us using this notation in here for now? Up and down with the understanding that this is living behind it and being really formal. Okay, so you guys, one more time, show me positive 1x to the first power. Yeah, do both hands, there we go. Awesome. Make it now with a negative leading coefficient. Whoop, it's this guy now, right? So we go here to here to here, and that's it. Okay, walk me through that, and I get all goofed up. As I go really far to the right, which way does my function go?
Up. Increase. Right.
Am I backward? Wait, hold on. Is this negative x? This is negative x, right?
Yeah. So you're.
Yeah, okay. As I go really far to the right, it goes downward. So check it out. If my leading coefficient is negative and my power is odd, it goes really far down to the right and really high up to the left. Just like this does on yours. Cool. Now, here's the cool thing. We are using x to the first to think about because it's easy, right? But I do want to pop over to Desmos real quick. I just remembered I said I was going to do this for your bell ringer, and I never did, but that's okay. Give me another odd number. Like f of x doesn't have to be x to the first. So we'll say 17x to the 38th. Yuck. That's an even. Let's not use 38. I might have misheard. Okay, 37 is an odd. Okay, so it probably does some wonky stuff in here, or it just looks dumb. I don't care either way. But check it out. Look at your table that we just made. If we have a positive leading coefficient and an odd power, as I move to the right, does it just get taller? As I move this graph to the right, what's it do? It doesn't care that it's x to the first or x to the third or x to the 37th. It follows the same rules. As I move really far left, does it decrease forever? Is that what our table just said happened? If I flip a negative, and we're going to make a different number. So we'll say it's negative, I don't know, 3x to the 5th plus 50 or 45, sure, x cubed minus 2. It's ugly, but let's check. There it is. Okay, it's a negative leading coefficient, right? Which, if we look at our table, negative leading coefficient and an odd degree, it goes up to the left. As I move really far left, and you can't really tell because it gets so steep, but as I move further left, which is what's happening, does it go up higher? Infinitely far left, infinitely far up. As I move further to the right and right and right, does it go down forever on this end? I'm only asking about the very outsides. I don't care about what goes on in the middle yet. We'll get there. But I can see that these same rules got followed. Everybody agree with that? Okay, what's the easiest even number you can think of? Show me the graph of x squared with your hands. And we're going to pause. That's a positive 1x squared, right? Even exponent, positive leading coefficient. If I'd said, I don't care what happens in the middle, only what happens at the end. Here I am. As we go really, really far to the left, what happens? It goes up to where? What about as I go really far to the right? Or left? I get my orders goofed up. But you guys, I think, just confirmed that it does this. Up to the left and up to the right. That's what an x squared would do. Now, this statement's even easier. If you want to write it, you can. I'm not going to require it. But as x, if it doesn't matter whether it goes to positive or negative infinity, can I just write one statement? How do I make it say it does both? Plus or minus infinity. F of x approaches what value? Good. All right. Last little sweet move that I bust out only at weddings. What if it's even and negative? What's a negative parabola? That's it, right? You like that one? Pretty cool. Down and down. That's it. Easy. Down to the left, down to the right. Okay. I get the vibe that you guys have talked about this before. Everybody remember in here? No. Do we need to talk more about it, or are you convinced it does this? Okay, I'm cool with that. All right. Now, eventually we will get to the point where we graph them, and that's really why we care about this right now. If I'm trying to graph a function, and I'm just going to do it in brown, don't write this, I just want to think about it. But if I asked you guys right now to graph this for me, f of x equals negative 3x to the fifth plus 2x squared minus 4x plus 1. Do you guys feel comfortable in graphing this by hand right now? No. However, can you tell me, without putting a scale on here, what happens at the ends? And I mean at infinity. Negative and odd. So I know negative x looks like this, and that's what I use in my head. So I know that at the end it does something like this over here and something like this over here. Which means all I need to worry about is what happens in here. So we've already simplified the problem, just for sketching purposes. If I wanted to fill in this information in here, what else would you want me to put in here? Like, do you think there's any points, and let's just check real quick. Am I guaranteed I'm going to have somewhere at least once where this happens? Convince me of that. How do you know that there's a root here? Are you less convinced now that I've asked you to try to convince me? Yeah. Don't be. It's a polynomial. It's continuous. It has to be. If I know it goes up forever, those look like positive values, right? If I was positive on this side, and I'm negative over here, and I'm never allowed to pick up my pencil, what number did I have to cross? We must have crossed 0, right? I can't go from positive y values to negative without crossing over somewhere where it's 0. Okay, that we will see again. That is called the intermediate value theorem. It has huge implications all over the place. Okay, so the big question becomes what goes on in here? And maybe there's like 3 or 4 or 5 roots that we would use, right? Like, can you imagine that these are all x-intercepts? If I knew these, would I have a better picture of my graph? Like, if I knew it was these, and I knew that it was negative here and positive, like I could get a graph out of this thing pretty well. It might not be perfect, but I would get a good idea of it. Our focus today, we already have this part, is we want to talk about that middle part. Before we talk about that middle part, one question for you. If there's one thing in life that you could experience, what would you like it to be? Here's what we're going to do. We're not going to go into super detail. All right, so we're talking polynomial functions. And so far, all we've covered is the end behavior that we can determine only based on the leading coefficient, whether it's positive or negative, and then the degree of that polynomial, whether the biggest power of x is even or odd. Those are the only things we have to worry about to know it's one of these 4 possibilities, always. Okay, beyond that, as we were looking at the graph here that I'd sketched, it's gone now, but the other big piece that we're going to need is we need to be able to find the zeros. Okay, there are 2 spellings. Whether you use the E or not, they're both correct. I will switch back and forth. Cool. We're going to talk about the zeros of polynomial functions. Now, wholeheartedly, one of the things, like we're always going to talk about zeros of stuff, whether it's in this class or calculus or any class you take beyond this. It was a pretty big focus in like any algebra you've ever done. There is a very specific part where zeros will be included in every class ever, but there's another thing that we're going to use over and over and over and over. So when we get to a new word that you've never seen, if you don't understand what we talk about and what we write on the board, you have to be really honest and upfront about it, because we're going to use it all year long. Okay, so right off the bat, we're just going to preface this and say that given a polynomial, and I'm just going to say poly, given a polyfunc, and we'll just call it f of x, we have a bunch, and I'm just going to say we have equivalent statements. Okay, and I think that I've heard and we've used this already this year, but there are a bunch of different things that we might be talking about. Equivalent statements. Now, each one of these depends on the particular context, but they're essentially, for lack of a better word right now, synonyms of one another. They are interchangeable. They mean the exact same thing. So here we go. The first of these, and these are in no particular order, but here's our first one. I'm going to use asterisk so it doesn't look like a negative or a bullet point. First one. X equals a for some number, we could say that this is a 0 of f of x. Okay, you guys have heard the phrase, the 0 of a function. I'm sure we've already used it this year, and everybody knows, I think, what I'm talking about. Do you remember any other ways that we talk about it? I could say it's a 0. X equals a is a 0. Is there another phrase that we could use? Okay, a solution, I heard. We're going to be a little bit more specific, but I agree with you. If we say x equals a is a 0 of f, another way to say that is x equals a is a solution. And I'm going to show you my shorthand. Solution for me is SOL apostrophe N. It's a Holloway contraction. Usha is the part that's in there. X equals a is a solution to the equation f of x. And what would we set it equal to if we're looking for the solution? 0, because it's a 0. This is just the solution to this equation. These are the same meaning, just slightly different language. Okay, can you give me another version of this? The root. I'm cool with that. X equals a is a root of f of x. Any others? What if we're thinking about a graph? What is the significance of a 0? The x-intercept. Now, I'm not just going to write x equals a as the x-intercept. If x is equal to a, what is the y value if it really is an x-intercept? So we would say then the ordered pair a comma 0 is an x-intercept. And I'm going to be really specific here. I'm going to say on the graph of f. But I think that's implied when we write it. But I just want to make sure really clearly, a0 is an x-intercept on the graph. Because if we didn't have a graph, it doesn't really make sense to talk about where it crosses the x-axis if there's never an x-axis to reference, right? We would use the phrase 0 there. All right, there's one more, and this one's going to be hiding. I'm just going to give this one to us. If x equals a is a 0, and this is arguably the most important here, then x minus a is a factor of f. Now, just to convince you of that, have you guys seen this language used for them? But check it out. If we got down, and I'm going to go here, this is just thinking, writing. If we got to a factorization of x minus 2 and x plus 3 equals 0, like we ended a problem, we got here to find the zeros, the roots, whatever you want to call it, everybody agree that this one gives us x equals 2. If x equals 2 is a root, here's the factor that it came from. Like you've used this always, you've probably just never highlighted that language. If x equals 3 is a root, negative 3 is a root, then x minus negative 3 is the factor, or x plus 3 is what it just came from. Everybody cool with those all mean the same things? Okay. Now, we have a fundamental idea showing up here in just a minute. I'm going to throw you a curveball, and it's not super because we've been doing a little bit of factoring, But I'm going to give you a single example. I'm going to let you guys get a head start. And we still have a lot of time. So we're golden here. But here's what I want you to do. I want you to find the solutions. Solutions of, we'll say f of x is a lovely cubic function. And it is equal to x cubed minus 12x squared plus 36x. Okay, I'm going to pause it. We're going to check your factoring stuff. I'm only going to let it go for like a minute maximum. If you can't solve it in a minute, that's okay. We'll talk about it. But talk it out with your neighbors, independently with yourself. If you talk to yourself, I'll give you about a minute. When I factored mine, and I assume you guys all did the same, I didn't look at your pages. Did everybody factor out an x? When I got here, we probably, our paths diverged a little bit. We did something different. You might have factored by grouping. Maybe. You look for factors of 36 that add up to negative 12. Did everybody do that? And you found negative 6 and negative 6. What did I do? Because I didn't do that. It's a perfect square. The same thing that we've been talking about with those quadratics. I noticed that this has a nice square root. So does 36. And that middle number, if I put them together, we get it. So here it is. Okay. Here's the big question. If I'm looking for the solutions, I'm going to set this equal to what? 0. And this is going to look silly for a second. What are the zeros of this? X equals what? 0 and 6. And here's where I'm going to move this over. I'm going to write downward, actually. Nobody would ever do this. And I totally make sense why you wouldn't. But do you agree that this is x times x minus 6 times x minus 6? And nobody would ever do that, I don't think. But I agree with 0, and I agree with 6. But notice what happens. That's a 0, that's a 6. What does this give me? 6. Now, have you guys ever written it more than once? If you haven't, or have, it doesn't really matter. You don't have to do it, but I want everybody to be very aware that it could show up more than once. There's a connection here. What degree was this polynomial?
3.
How many roots did we just find?
3.
Although one might claim 2, there's really 3 of them. It's 0 and 6 happen to repeat. That's okay. Okay, here's the bigger piece of this. Last thing that we're going to talk about today. This happens fairly often, these repeated zeros. Like, it's a pretty common thing to occur. Has it ever meant anything graphically to you? Like, does it matter that it repeats? We're going to play around on Desmos for just a second. I'm just going to grab functions, and we're going to let it, I don't even care about the actual function. I'm going to make it so we can see it. You guys are going to give me some factors, and we're just going to see if it repeats or doesn't. Is there something specific that happens? So what's your favorite linear factor, Dolan?
3x.
Okay, so if we have a 3x, so let's just knock it out. I'm going to write this in factored form. Let's say we have a factor of 3x, and another factor is x minus 1, and another factor is x minus 1. We had a repeat, yeah? Okay, check it out. There are 3 zeros here. Do you guys agree with it? It's 0, 1, and 1. Cool with that? How many times did x equals 0 show up as a solution just now? Once. And how many times did x equals 1 show up? Okay, so check this out. On my graph, if it showed up one single time, what did you say my graph did here? So it is increasing. It crosses the x-axis. What if it shows up twice? Does it really cross it, or does it just touch it and then turn back around? Like, one example does not make this work, right? But let's try another one. Can we all agree that it looks like maybe if it repeats, something specific happens with the graph? It bounces. I like that language. Okay, let's do g of x as well, and we'll see what color this is. Let's do another one. Let's say it's x squared, which is really x times x. So there's 2 factors there. Oh. Interesting. When I graph x squared, do you agree there's really 2 roots, and they're both 0? What did my graph do when it hit that 0? It touched and turned back around, yeah? Okay, well, what if we do something crazy like x times, I don't know, x plus 3, what? Plus 3, and x plus 3, and x plus 3. That repeats again, right? So we have 4 roots. One of them's at 0. How many times did the solution x equals 0 show up? Once. And when it shows up one time, what did my graph do? Or cross that 0? Did it cross or touch and turn around? It crossed. I'm going to change my language because I like the bounce more. I'm going to use bounce. Okay. It crossed when it showed up in one time. When it showed up 3 times or thrice, did my function cross or did it bounce? Did it? Here I'm positive. Here's my root that shows up 3 times and it crossed. If it shows up an odd number of times, we cross. If the root shows up an even number of times, we bounce. Now, before I see you guys summarizing it, and I love that you're summarizing it, hate that I lost my stylus, love that I found it, all over the place. Here we go. We're going to introduce a word. Okay. You will hear me say this word. It is an ugly word, but we're going to get it. Okay. First off, when we're talking about the roots, one of the natural things that happens is what we just encountered. It's where we talk about repeated zeros. Now, I don't care if we think about this as repeated zeros, as repeated factors. It doesn't matter. Whatever language you want to pick out of those equivalent statements, it repeated. Okay. Here we go. We're going to think in terms of factors. When, or a factor that repeats k times, and I'm just going to put a e.g., so an example of that. We can think of a factor of maybe it's x minus some number a, and if I wanted it to be showing up like 3 times, I could write x minus a and x minus a and x minus a, or when I multiply by the same thing over and over, k times, can we agree it's just to the power of k? So just like we did on the one on the graph here, x minus 3, or x plus 3 rather, if I graph this one, it is the exact same thing as if I graph the function that is y equals x times x plus 3 to what power? How many times did that factor show up here? So when I graph this, is it a different function? No, they're the same. This is a nicer way. Okay, we've seen this happen. It happened just now. A factor that repeats k times, like this, has or is said to have, and here's our new word, a multiplicity of k. You will hear me say this word for the rest of the year in here. You will hear me say this word, and it becomes really valuable to know this when we get to calculus, because it turns out if you remember this rule that we're about to write down, so many things get so easy. Okay, multiplicity. It's ugly, but we can see it's just how many multiple times did it show up. That's all it's after. So here's the rules. You guys just had it. So a little follow-up. If your multiplicity, which we just wrote it down as k, if k is odd, the graph crosses the x-axis. All right. No matter how much I like the phrase it bounces, I'm going to say touch and turn, and it's going to happen because I've used that for the last however many years I've taught. Okay. If k is even, the graph touches x-axis and turns around. If you guys want to write bounces, I'm fine with that. It touches and turns around. Now, where we're going to see this really helps us a lot is when we try to solve inequalities. So if I have a function and I want to know something gross about it, and I don't need you to write it down, but do you guys agree that this is kind of a gross factorization if we had to get to it? Like there's a function whose factorization is that. Okay, if I wanted to know where is it positive or negative, which is a pretty common thing that we might ask, I know that it can only ever change sign if it's at the x-axis, right? That's the only place it could ever change. We could then take these roots and plug in on the x-axis. There's a -2 and a 0. And then check this out. Hypothetically, if I were to plug in a 1, I know it's positive. And I just plug that in 1 times 3 is positive. Everybody okay with that idea? How many times does x equals 0 show up as a root in this one? So if it was an 1, that's an odd number. If it was positive and then it crossed the axis, what is it here? It was positive, and if it shows up an odd number of times, it crosses the x-axis. So if it was positive and it crossed the x-axis, now it must be, and all of a sudden I don't have to evaluate my function anymore. If it was negative and then it got to this 0 that had a multiplicity of 2, it touched it and turned around, yeah? Which means it's still, we were going to use the heck out of this. If it didn't click just now when we did it, we will use it. All right, there's no homework tonight. We have a meeting at what time? 12:40. We'll see if who shows up. I know people will. All right.
We're going to Pumpkin Day? Yeah.
I think there's presentations about the theme as well. If we don't get to the vote today, that's okay. But if we have a bunch of presentations, maybe we need time to see them.
Okay.